Hi everyone. For chapter 13, we are going to focus our attention on chemical equilibrium. And for the theme of chapter 13, we are going to take a look at how far the reaction goes. Okay, so to compare with the previous chapter section that we learned about chemical kinetics. So chapter 12 is talk about how fast the reaction proceed, right? So whether it's proceed slow or fast. But in this chapter, we are going to take a look at how far the reaction proceed, which means how far or how much product can be made, right, for a chemical reaction. So the theme of this, we are going to focus our attention on the dynamic equilibrium. Okay, so we are going to use the term which are reaction quotient and also equilibrium constant to help us determine how much substance that are in equilibrium. Okay, so that's kind of like going to be the theme of this chapter. So this video, we are going to focus our attention on the concept of dynamic equilibrium first. Okay, so let's establish this concept so that way we are able to understand the following concept better. Okay, so this section is going to be part of the OER textbook, chapter section 13.1. Before we get into the chemical equilibrium, I would like to use the migration as an example to help explain this concept a little bit easier, so that way you are able to grasp the concept of dynamic equilibrium better. Okay, so let's say that we have two countries, okay, so A and B with different population. Okay, so at initial state, okay, so I'm going to give this at time equal to 0. Let's say like at this point, we have high population in country A than country B, right? So eventually these people want to migrate to country B, right? So probably be just to find different resources and things like that, right? So in this case, some people would migrate. Okay, so that means we have the rate going forward, okay, to country B. So if you think about this, right, so people, because we have high population in country A, so therefore there are going to be a lot of people that is going to want to move to find more space, right, in country B. But at the same time, some people who already moved to country B might not actually like it. So that's why they are going to end up moving back to country A. Okay, so that's fine, right? So sometimes there will be at the beginning, since you have high population, so there will be more people to move into B, right? And at the same time, some people that already move into B might not like it, so they are going to move back as well. But if you let this happen, eventually at this time infinity, which means at the time that you are going to see that the rate going forward and the rate going reverse, which means the migration moving in and out of country B is going to start to be equal. Okay, so these people that moving in and out start to be equal. This rate right here, we establish that the rate going in is equal to the rate that going out. This is what we refer as dynamic equilibrium. Please note that at dynamic equilibrium, the number of the population between the two countries doesn't have to be equal. The only thing that needs to be equal is the rate that people moving in and out. Okay, so to tie this back into chemical reaction, you are going to observe the same thing, right? So if you give this as the reactant and if you give this as the product, you are going to observe that at equilibrium, you are going to see that the rate going forward is going to be the same as the rate going in the reverse direction, but the amount of the product or the reactant doesn't have to be the same. Only the rate that are going to have to be the same. Okay, so now I'm going to tie this back into chemical reaction now. Okay, so what does it mean? Okay, so dynamic equilibrium is going to occur with the reaction that is the reversible reaction. Okay, so that means it can go forward and also it can go reverse as well. Okay, so if you're looking at plotting the graph between the concentration and time, okay, so think about this, right? So at the beginning, so similar to what we see between country A and B, right? So at the beginning, you have only population in country A. So same thing here. At the beginning, you are going to have only the reactant, right? Because they have not reacted yet. Okay, so you are going to end up with only the molecules of reactants. Okay, so that's why if you're looking at this, right? If you have hydrogen as blue dot and iodide as red, you are going to see the high concentration of hydrogen and iodide on the y-axis at the high concentration. Okay, so and because at the time 0, right, so you have not produced any product yet, so therefore the hydrogen iodide gas, right, is going to have a 0 concentration for that. Okay, so that's at the beginning of the time. Okay, so now what happened then? So as I mentioned earlier, right, so at the beginning, right, so if you go back to that migration picture, right, so you're gonna see that because it's have high population in country A, there are going to be more people going from A to B, right? So that means in this case, you are going to observe that a lot of what do you call concentration of reactants, they are going to deplete quickly because there are a lot of them to react, right? So as they react, they are going to deplete, right? So because they are producing more and more of the product, so the rate is going to slow down. Okay, so this is tied back into chapter 12, right? So why is it slow down? Well, if you're looking at chapter 12, right, as the concentration of reactant decrease, right, it's going to cause the rate to decrease as well because it have less molecule to collide, right? So according to the collision theory, so therefore the rate is going to be is going to go slower, right? So as you see here, the rate is going to slow down up until that you probably notice that the slope of this, right, is going to get less steep as time go by. Okay, so the reason for that is because as the amount of reactant decrease, right, so the rate will also decrease as well. It's going to this is going to happen up until you are going to reach the time where the concentration of the product and the reactant are no longer changed. Okay, because they are so what does it mean? Okay, so this means that because you are producing more and more of the product eventually, right? So some of the, because this reaction is reversible, so that means some of the product can also what do you call reverse back to the reactant as well, right? So that means in this case, once some of the product that reverse back to the reactant, the rate of the reverse equal to the rate of the forward, right? So you are going to observe that the concentration of these two, right, the reactant and the product will remain constant. Okay, so whenever this concentration of the product and reactant remain constant, this is when we call dynamic equilibrium. At this point right here where the concentration remain equilibrium, right? So this is what we call dynamic equilibrium. Okay, so this is when the rate of the forward equal to the rate of the reverse. So how do we know when a reaction has reached equilibrium then? Okay, so the answer is going to be when you observe that the concentration of the reactant and the product remain constant. Okay, so they no longer change. Okay, so as the time progresses. Okay, please note that this doesn't have to be the same. Okay, so when the reactions stay constant, it doesn't mean that they have to be the same. So as you observe here, for this particular reaction, right, so the product actually has higher concentration than these two reactants. All right, so for summary of the dynamic equilibrium, okay, so it's not static, right? So it's happen back and forth all the time. So it's going to happen when the rate of the forward equal to the rate of the reverse. And when the dynamic equilibrium has reached, you are going to observe that the concentration of the reactant and the product are no longer changed. Okay. However, these concentrations are not necessarily equal to each other.